Welcome back to the second in this series of lessons about how to find the shortest path through a data structure. In this lesson, you'll learn about Dijkstra's algorithm. First of all, you'll find out what Dijkstra's algorithm is, and then we'll go through a worked example carrying out Dijkstra's algorithm on paper. And then I'll set you a series of challenges so that you can do Dijkstra's algorithm for yourself. The word Dijkstra is the name of a Dutch mathematician who is still alive and has invented a lot of great things in computer science. And one of the things he did was to invent an algorithm which could be used to create computer programs to find the quickest route through a map or graph data structure. And it's called Dijkstra's algorithm after his name. The way that Dijkstra works is it looks for the shortest path outwards from a start node, and it keeps finding and recording the shortest paths outwards from the start node in all directions until one of its routes actually reaches the target node. Remember that computers don't work like humans. If we were looking at a map, let's say of the country, we could stand outside the map, look at all the places and see very quickly what was the right route to go from one place to another. A computer doesn't do that. It just looks at one comparison at a time. And so Dijkstra just finds all the routes in all directions. It can do that because computers work so quickly, but it doesn't use a big picture. An algorithm like this, we call it a greedy algorithm. That's just sort of a computer science nickname for it. And a greedy algorithm is one that always picks the easiest or shortest solution at each step. And it doesn't plan several steps ahead. It just takes the easiest decision at each point. So we're going to do this on paper now, and hopefully that will help you to understand what's happening. Each time we'll be picking the shortest distance. We won't be looking ahead and thinking, oh, this will take me in the right direction, or this won't take me in the right direction. We just pick the shortest route every time. So we're going to do Dijkstra on paper, and that's what will come up in the exam. You don't have to write a program to do Dijkstra. However, if you're interested in it, I have some extra material on this, so we'll do that separately. But in this presentation, we'll simply do Dijkstra on paper. When you do Dijkstra on paper, they'll give you a start and target vertex. You record all possible paths from the start vertex and pick the shortest one each time. When your shortest path reaches the target vertex, you've found the route from the start to the target. And we'll record this in a table on paper with paper and pen. You can follow along this at home as you're watching this lesson. So I'm going to talk through this example, which is about the simplest map that I could find. And the challenge is to find the quickest route from A to B. If you're set a challenge like this, the easiest way to do it is to create a table like this. There are more complicated ways of recording Dijkstra, and in the maths department at Keck, they do it in a different way because that's the requirement of the maths exam. But for computer science, we can do it in a very simple way. It works, and all we need to do is to record 3 facts about each vertex or node. So what I always do is create an empty table like this. I look at the nodes, I in this example, there are 4 nodes, so my table has got 4 rows, and I write in the names of the 4 nodes. And then I'm going to record 3 facts about each node. What node links to it, what the total distance away from the start node is, and the status of the node. And that just means, is the node cleared? Is it active? Don't worry about that at the moment. I'm just going to explain how we use that over the next couple of slides. So first things first, let's say you're given a question like this in the exam. Look at the map, count the nodes, create a simple table like this with a row for each node and write in the names of the node. Doesn't matter what order you put them in. For simplicity, I've put them in alphabetical order. Now we're trying to find the shortest route from A to B. So we always start with the start node. A is the start node, so we're not linking from any other node. And the distance from the start obviously is 0 because it is the start. And it's the active node, so we'll write active in the status column. You could use a tick or an asterisk or something, but I'm going to use the full word. So A is my active node. Once we've picked an active node, we then try and find all the routes from that active node. So where can we get to from A? And clearly we can get to B or C. So in my table, I can get to B from A, I can get to C from A, and I can fill in the distances. The distance from A to B is 6, and the distance from A to C is 3. That's it. I've now finished all the work with node A. So node A is no longer the active node. I'm going to mark it as done, or you could put a cross there or whatever. And that just tells me that I'm not going to visit node A again. So in all the rest of the calculations, I'm going to just ignore node A as I continue to fill in the table. So let's just recap. The first active node is the start node. We find all the nodes we can get to from the start node and fill in the distances, and the node is now done. Now we've got to pick our next node. What we do is we look down the distance column and we find the smallest number, leaving out any nodes that are done. So pretty clearly, the smallest number is 3, and that means that C becomes our new active node. We repeat what we did before. We find all the places we can get to from C. What's the answer to that? Have a little think. So the nodes that we can get to from C are A, B, and D. A, we don't revisit. We never go backwards. So we're not going to go back to A. A is done. So that leaves us with B and D. So let's go through those one at a time. From C to D is a route of weight 1. But what we write in is the total distance. So don't forget this. In the distance column, we write the total distance from the start node. So from the start node A to D is 4. And an easy way to do this is to look at the weight at C. The distance at C is 3, and add on the extra distance from C to D. So 4. So recap. The distance column shows the total distance from the start node. What about B? Well, the total distance from A to C to B is 7. The distance from C to B is 4. C already has a distance of 3, so adding them together, that makes 7. We don't write that in because that would make it longer. That would mean we're adding a longer route to the table, and the whole point of Dijkstra is to find the shortest route. So if we ever find a route that's worse, we don't write it into the table. And now we finished node C. And so we write done into node C, and we won't ever revisit node C again. We have to pick the next node to become the active node, and it's D. Clearly because node D has the smallest value in the distance column. A has the value 0, but it's finished. C has the value 3, but it's finished. Of the remaining nodes, D has the smallest value, so it becomes the next active node. So let's go back over how we do this. We've got an active node. We find every route out from the active node. We fill in the total distance, remember the total distance, but we only replace it in our table if we found a quicker route. And when we've finished with a node, we mark it as done, and the node with the new smallest value becomes the next active node. And then we'll just repeat this process until we've done all the nodes and found the quickest route to the target node. So let's quickly complete this task. So node D is active. There's actually only one remaining route, which is the route from D to B. So node D has got value 4. The distance to B is 4 plus 1, because the route from D to B is 1. D has the value 4. Add 1 gives us 5. And what can you see about 5 compared to the route that we've got written in at the moment? We can replace this data because it's a smaller value. We found a quicker route, so we can replace. Obviously, because I'm doing this on using PowerPoint, I'll just delete and add it in. In the exam, actually cross it out. Leave it so that the examiner can see that you had the data there and you've crossed it out so that they can see that you've done the correct work. Don't scribble it out or use a rubber or anything, because that's part of your workings. So I've replaced it. So instead of a link from A with the value 6, it now says a link from D with the total value 5. We've now completed Dijkstra and we've found the shortest route to B. So this shows you how it's not drawn to scale, because if you were just looking at it by eye, it looks like the quickest route is A, B. But actually the quickest route is to go A to C to D to B. When you're writing the answer down, that's how you would write it. You would write the full route. And we can find the full route, even in a quite complicated diagram, by going backwards through the table. So B we get to from D, D we get to from C, and C we get to from A. Write that down, A, C, D, B. And the distance, which we can just see on the table there in the distance column, is 5. And that would get you full marks in the exam. Remember to show your working. So if you replace a value in the table, cross it out in such a way that the examiner can see what you've done. So let's go through Dijkstra's algorithm one last time. The node with the smallest value is the active node. When you begin, that will be the start value where the distance is 0. So the node with the smallest distance value becomes the active node. Find all the nodes you can get to from the active node. Calculate the total distance and write it into the table. However, only replace what's in the table if the value is smaller, if you found a better route. Once you've done that, the node is done and we won't use it again. Keep doing this until there are no more routes to the target node. And then whatever is in the table will, by definition, be the shortest route to the target node. And you've completed the task. Now that you know how to do Dijkstra, I'm going to set you 3 exercises. I'm not going to give you the answers as part of this presentation. If you're my student, I'm going to send you a worksheet with these tasks on them, and you can complete the worksheet and send it back to me. The first task is to find the shortest route from A to F in this map. The next task is to find the shortest route from A to G in this map. And because this is quite a complicated map with several nodes, you could set yourself another challenge and try and do it yourself if you want more practice. And then this is the final task, and this is a bit unusual. It's a directed graph. It shows airplane flights between selected airports in the USA. And as you see, the arrows show which direction you're allowed to go in. So, for example, there's a flight from Dallas to Denver, but there isn't a flight back from Denver to Dallas. Obviously, I know in real life there would be, but for the purposes of this exercise, these are the only routes you're allowed to take. And the weight, I think, represents the number of miles or kilometers between those locations, doesn't matter. And your challenge is to try and find the shortest route from Dallas to Washington, because you can see there isn't a direct flight in this example from Dallas to Washington. So what is the quickest way? And use Dijkstra in exactly the same way, but just remember you're not allowed to go on routes against the arrow. So try that one as your third and final challenge. Send me the work. If you're my student, send me the work and I'll mark it for you. Okay, take care.